Today we're going to talk about an engineering application of neural nets, which is system modeling. If you have a engineering system, can you model it with a neural net? And to illustrate this, I'm going to look at a simple robot arm. So this is a rotary robot arm. So imagine, in fact, I think we talked about this. Yes, we did. When we talked about scaling data. So this is an arm that can rotate about the origin of an x1, x2 axis system through an angle theta. The arm has length L. And we want to track the position x1 and x2 of the end of the robot arm. So this is a real simple mathematical system. x1 is equal to L cosine theta. x2 is equal to L sine theta. So there's our equation model. And if we think of this as a block diagram, we put in a value of theta, and inside here are the equations, and out we get x1 and x2. So let's say we wanted to model that with a neural net. Looks pretty easy. Theta is the input, x1 and x2 are the outputs, and so we would have a neural net that would take theta as an input, and that's a linear neuron here, so it passes theta through. We put a weight value of 1 and 1 here. We make a neuron here that has a cosine activation function, and this one has a sine activation function. The weight here is L. And then we have linear activation neurons here, and we get out x1 and x2. So this is a network that's tailor-made to the particular problem. And it works real easily, but it's not a general approach. Because every time we have a different system, we have to recreate and figure out, well, what does the network look like to fit that system? So a more general approach would be to say theta is the input. We have some hidden neurons. Maybe they're 10H. We could even add another layer here. Fully connect this whole thing. And then have output neurons. We scale the data like we talked about, and we train with a set of data, and we can get a general neural net. We'd have to figure out how many hidden neurons we put in here, but this approach would be more general on modeling a system where we know what are the inputs to the system and what are the outputs. Just like we did for the iris problem, we needed to know what were the measurements that were correlated or connected to the classifications. And so that's a general technique. But there is something to be learned from this tailor-made neural net, is that activation functions used should fit the problem. In other words, like the case above, if you know that the data is going to be analyzed and modeled by sines and cosines, we'll put those kind of activation functions into the neural net. All right, so that robot arm was a static problem. meaning it's not time varying. So let's kick it up a notch and look at a rotary robot arm, but now instead of being a static system, it's a dynamic system. So here we have the same arm. But now it's dynamically actuated or forced with a torque. So that's a moment applied to this end, and the torque can be a function of time, and that means that the angle of the arm will vary with time. Maybe we start the arm out with an initial condition down here, then we apply a torque, and it's going to move around through that time. More torque, that means theta is going to change faster. So the equation that fits this problem is that J, which is the mass moment of inertia of the arm, the rotary moment of inertia, times d squared theta by dt squared is equal to the torque. And we're going to define an intermediate variable. We're going to define omega to be the angular velocity, and that's going to be d theta by dt. So if we want to, we can write the differential equation that describes this as j d omega by dt is equal to the torque that's applied. So how do we model this kind of a system with a neural net? What we've got, as far as a block diagram goes, is we've got the torque as a function of time, goes through the differential equation, which means we have to solve that differential equation, and out the other side come the functions of time theta and omega. And also, if we want, we can talk about x1 and x2 being functions of time, because the position of the arm is going to vary with time as theta varies with time. But how do we use a neural net to do that? This is not a value, this is a function of time. This is a function. Whereas we need numbers for our neural net. So the approach is to do what's called a discrete time system model, or a discrete sampled time. So we're talking about sampled data. And it really involves just using the definition of a derivative from calculus in discrete delta t time steps. So if we say delta t is a small time step, then the derivative, the differential equation, we put the j on the other side here, can be approximated. The derivative can be approximated as the difference over a small time step divided by delta t. That's just the definition of the slope of a function or the derivative, and this is an approximation because we're not taking the limit as delta t approaches 0. If we did, then we get the derivative. That's the definition of the derivative. All right, so we do this approximation, and there's our differential equation. And then if we look at the formula for omega, or for theta, we have this, and so we difference this derivative. And then this tells us what data we need to send to the neural net. We take this equation and we solve for theta at the next time step, delta t ahead, and we solve for omega, and we shove everything else that has t in it over to the other side. So divide by delta t here, rearrange the equations, and we get omega at t plus delta t is equal to omega at t plus delta t over j times the torque at the time t. And then we get theta is, I lost a delta t here. Yeah, the delta t has to go here. So what this does is it says, well, if I want to predict what omega and theta are one time step ahead of the current value, this is the data that I need to send into whatever it is, whatever black box, whatever function is going to calculate these new values, and that gives us our neural net. And then what about x1 and x2? This simply says, yeah, we need this data to predict the new x value, which means that we need the same data here going into the neural net if we wanted to predict this value. And the same thing for x2. So if I want to predict x2, I need this value, and that value comes from here, and so we simply know that these are the data that we have to send in to the neural net. So let's draw a picture of our neural net that's going to do this. So the neural net, looking at the data here, we need omega at t, and the torque at time t, and the theta at time t. Makes sense, right? If we want to know where the arm's going to move, we need to know, well, how much torque are we putting on it? Where is it now? Where is it now, which is theta, and how fast it's going right now. And this is how much extra omega we get per time step. So those exactly are the inputs. All the values at time t are what go into our neural net. So let's draw a neural net with 3 input neurons. And in these, we're going to send in the torque at the current time and theta at the current time and omega at the current time. And then we're going to throw some hidden neurons in here in order to do the proper mapping. We can have as many layers as we want. Typically 1 or 2 layers is all you really need for something like this. Fully connect it like this, and then the outputs are going to be whatever values we want to predict at t plus delta t. And I'm going to list all 4 here. We're going to calculate theta omega x1 and x2. So how did we figure all this out? How do we know what needs to go in? We started with the differential equation here, and then we differenced that, and then the differential equation needed the definition of theta, so we differenced that, and then we rearranged it so all of the t plus delta t stuff's on this side, everything else is on the right, and so the whole list of things on the right gives us what our inputs are, and the stuff on the left at t plus delta t are our outputs from our network. So that's how we would create the network, and this is our model. So this is an artificial neural net model of our dynamical system. And you can do this with any dynamical system that is a function of time. You have to look at it, and if you have differential equations, you can difference those and look at what depends on what. Otherwise, you simply have to talk to somebody that knows how the system operates and find out, well, what are the current values that we need to feed in, and what are we trying to predict? With a neural net, we need to collect data to train. So here's how we do that. We choose initial conditions for our robot. So we would choose theta at 0, omega at 0, x1 at 0, and x2 at 0. Well, if you think about it, if we were going to solve that differential equation, we would need initial conditions in order to figure out the solution. So this makes total sense. And then let's list a table. So let's make a table with collected data. And we list theta, omega, x1, x2 as a function of time, and then we apply a torque. We can apply constant torques, we can apply torque time histories, we apply different torques, and then we simply collect the data. We start out at our initial condition, and then we run the system forward in time. It's sitting here on our table, we apply the torque, and we can measure all these values. So then we collect theta at 1, at delta t. So 1 time step ahead. And we keep going. So then we have theta ahead at 2 delta t. And we keep repeating this. Every delta t time step, we collect data. So we end up with a whole string of data that we collect. And maybe this is all for one particular torque. Torque time history, let's call this torque time history A. And then we could do another torque time history and maybe different initial conditions. And we'll call that B, and so we get more data here. And we can apply all kinds of different torque time histories and collect data. So what do we do with the data? This is going to become our training data, and what we need to do is rearrange it into current time values and next time values from the data. So the inputs, let's say for just one training pair, we're going to grab these values here. And we also need our torque, so we should have listed in our table the torque as a function of time. And here's the torque at time 0. And here's the torque at time delta t. So this is just a listing of the data of our torque and how it varies with time. And this is the data that we collect for the neural net. Those are the inputs. And then what are the outputs? Let's go back up and look. The outputs need to be the values at the next time step. So from our table here, the red circle stuff is our inputs, and then our target outputs are going to be these values here. So that would be the first line in our data set for training the net. So how about for another line of training data? I'm going to try to find another color here. Choose blue. The inputs for the next time step are going to be these values. And then the outputs, the target outputs, are going to be these values. So we're just grabbing the data that we need. I forgot to circle the torque here. There's our inputs for the next time step. Here's our outputs. And we just shift down through the data, creating training pairs for our neural net. So a typical training pair would be what I've listed already. We would input the torque at 0, theta at 0, and omega at 0. And so those would be the inputs. And then here's our target outputs, which are theta at the next time step, omega, x1, and x2. And then we would do another one. This is the torque at the next time step. And another time step ahead, we do this. And we keep doing that. So all this really is a rearrangement of the data that we collected from the actual system. So this neural net would model the system that we experimentally collected this data up here. So that's how you could use a neural net, an artificial neural net, to model a physical system even a dynamical system, and this could be done for a robot arm like we did, maybe a multi-joint robot arm. We could do this for an aircraft. We could do this for a chemical system. Let's say a distillation column. A biological reactor. All of these are dynamical systems. Or even a tractor trailer truck. Backing up to a loading dock. And by the way, this list comes from a lot of work that we cover in another class that is focused just on system modeling and control. So it's not neural nets or machine learning, it's system modeling and control with neural nets. And portions of what I'm teaching you in this class come from this class, some of the introductory material. And in that class, we do a lot more. We do system modeling, and we also talk about, well, how do you control a system with an artificial neural net that learns or adapts.